Alrighty then, this is my last little bit that I didn't get to finish on the last video. Quantized wave functions and orbitals and stuff. I should take but a few minutes, I hope. Geez, I could go on forever about this stuff. Because indeed, further courses in chemistry in undergraduate chemistry do indeed take a full semester to talk about all these details. Not necessarily just the hydrogen atom, but it can go on for a while. Keep in mind this, that within each orbital, this one and 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 this one, each orbital, no matter how complicated looking, holds exactly 2 electrons, or 2 electrons are allowed to exist in that orbital. Sometimes the orbital is represented by a line or a box, and those 2 electrons are represented by an up arrow and a down arrow. This m sub s quantum number is the spin quantum number, and it turns out electrons sort of spin like tops. One of them spins in one direction, the other one spins in the other direction, and we describe that by either this or this, but easily like this. So every orbital, no matter how funky looking or simple, always holds 2 electrons. So what's the moral of the story? If I put many of these together, and the small ones, get bigger, and the small one's closest to the nucleus, and then it gets bigger and bigger and bigger and bigger, that if I nestle them all on top of each other, it looks like a huge spherical mess, so that I can't really, it's hard to distinguish. And then in a sense, that's why it ends up the atom ends up looking somewhat spherical, or not looking, behaving spherical, because of all that. Also, sometimes important are the phases of these orbitals. The phases, like phase of wave. A wave could, like a sine wave, could be up or down, up or below a particular axis in a positive or negative direction. And so too can these wave functions describing the orbitals have a phase to them. The s orbital is almost too simple. It could either be positive or negative. That is, L equals 0. But the p orbitals could have almost always a positive and a negative, not almost always, as far as I know, always a positive end and a negative end for any one orbital. 2 electrons can fit here, 2 electrons can fit here. The p orbitals are very similar. P orbitals means L equals 1. 2 electrons can fit here, 2 electrons can fit here, 2 electrons can fit here, and this one and this one and this one are all nestled on top of each other. And positive, negative, negative, positive. So that when these orbitals come together, occasionally the positive and negative will reinforce or can do some cancellation, help each other out or go against each other in a sense. So this has d orbitals, positive lobe, negative lobe. 2 electrons can exist in this orbital, and one of them has to be spinning up and the other one has to be spinning down. Interesting. I didn't even bother to mark the f orbitals plus and minus, but this next diagram does. Again, f orbitals is L equals 3. Here's the positive, negative on that. If we care in terms of phases, it looks like positive and negative, and positive and negative, positive and negative, and positive and negative, and you get the idea. Here's a cool diagram ranking the energy levels of the orbitals. So if I was, say, a level 4 or level 5 is big enough to have f orbitals, this could be the 4s, the 4p, the 4d, and the 4f. These are a little bit larger and higher in energy, a little bit smaller and lower energy, a little bit. When I say a little bit, I mean a little bit. Higher in energy, lower in energy. But this one and this one and this one and this one and this one, all energy levels all have the same energy, and they're said to be degenerate with each other. So there's none of these 7 orbitals, f orbitals, are any higher in energy than any other in a normal unbound atom. And I could say this one and this one and this one and this one, those are all degenerate with each other, same energy level, but they're all slightly higher in energy than these, which are all slightly higher in energy than these, which are all slightly higher in energy than that. Alright. Other cool pictures I found on the web, worth looking at, thinking about for a second, other ways to say it. Let's see, this L equals equals 0, L equals 1, maybe M sub L equals negative 1, 0, or positive 1. L equals 2, M sub L could be negative 2, negative 1, 0, positive 1, or positive 2. L equals 3, that's the F orbitals. It could be M sub L equals negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3. Crazy. Here's a cool fuzzy picture, and it's fuzzy on purpose because they're trying to remind us that when we're talking about these orbitals, we're talking about fuzzy regions of probability, whereas if I were to take a million snapshots of the existence of the positions of the electron, it would kind of end up looking kind of blurry in terms of so many positions and little point sources. But then again, maybe it's best not to think of the electron as a point anyway. Maybe it's best to think about the electron as a wave. So here's something we'll go into more in the next video, but I don't have that much more motivation for this one. I said I'd finish. Geez, I'm already 6 minutes into it. Yeah, these electrons all belong to what we call the s block. Their outer electrons are all filling in s orbitals. And for this particular case, I could put the helium right over here as well, because hydrogen and helium are filling in their 1s orbital, and that would be lithium and beryllium filling in their 2s orbital. And is it sodium? Yeah, sodium and magnesium filling in their 3s orbital, and potassium and calcium filling in their 4s orbital, 5s. It's called the s block. Over here, after the s block, I think about the p block. 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So these elements are filling in their 2p orbitals with electrons, and we call those outer orbitals the valence electrons. This is the d block. These elements like manganese and iron and zinc and copper are filling in their 3d orbitals, and the outer electrons are the 3d orbitals in most manners of speaking. And this is the F block with the really large ones like uranium and plutonium and such. They're filling in their 4Fs and their 5Fs actually right in here, sometimes even before the 4F might fill in before the 5D. We'll talk more about that. Oh, I love this poster. Call me a nerd. I call myself a nerd. Proud of it. Maybe I'll zoom in, make that a little bit bigger. I hope this comes out well. This is the S block, and I have hydrogen and helium, lithium, beryllium, sodium, magnesium. 2 electrons can fit in each orbital. Look at the shapes. Small, this is the 1s, this is the 2s, 1s, 2s, 3s, 1s, 2s, 3s, 4s, 1s, 2s, 3s, 4s, 5s, 1s, 2s, 3s, 4s, 5s, 6s. So really this is larger than this, which is larger than this, which is larger than this. So this thing gets shrunk down to here, and this whole thing gets shrunk down to there, and this whole thing gets shrunk down to there, and this whole thing gets shrunk down to there. So this is not to scale. So this is the largest, and that's the smallest. Look at the p blocks. I got the m sub L equals negative 1, 0, and positive 1. And 2 electrons can fit in this one, 2 electrons can fit in this one, 2 electrons can fit in this one. And then similarly the d block with that would be L equals 2. If L equals 2, then m sub L could be negative 2, negative 1, 0, positive 1, positive 2. And again, 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons. So if I put 2 electrons in each of these, that gives me 10 elements. And you'll notice in the d block of the table, there are 10 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. Again, I absolutely love this. I wanted to get a poster of it, but it was too expensive, and I'm a tightwad, so I didn't buy one yet. But I like this illustration quite a bit, because that fits into this in a way. You can imagine nestling it down there. This is very interesting, and you should study it sometime with the quantum numbers and what they might look like for any particular element, any particular electron in a particular orbital in a particular element. And as you can imagine, that could get kind of messy. What else do I have? Oh, other listings here. So take a look at this. I don't know how much I want to get into it now. As I said, I'm almost 10 minutes into this, and I'm almost out of my slides. But this is the principal energy level, 1, 2, 3, 4, 5, 6. These are the L spherical, spherical, dumbbell, spherical, dumbbell, double dumbbell, spherical, dumbbell, double dumbbell, quadruple dumbbell, and oh my goodness, F orbitals. I can't even describe what they look like, but you saw the pictures. Only the very largest elements need F orbitals. So yeah, there's no orientation of the s orbital. It's just around there. But there's orientations of the px, py, and pz, px, py, and pz, and there's orientations of the d orbitals, and they have their specific names, labels as well, d sub whatever. But I really don't think you need to worry your little heads about that. The interesting one is the dz squared. That's kind of cool with along the z-axis and the donut in the middle, that torus thing. Alright, I think I'm going to shut up here and let you guys go practice this a little bit on homework and discussions. For heaven's sakes, go to your discussions and we'll do more examples of this. Yeah, thanks again, guys. See you in class.